We are going to talk about some real-life applications here. Well, of course, all of these have real-life applications, but this is a really real-life application. Electric generators and motors. Electric generators induce an EMF by rotating a coil of wire in a magnetic field. Okay. So here we have a fixed magnetic field from magnets. We've got our loop in here, conducting loop, and it's being rotated by a person or by some other mechanical means, and then that rotation generates an EMF. Now, because the wire loop is constantly moving inside this magnetic field, the induced EMF and likewise the induced current is going to be fluctuating that whole time. Now, only the sides of our loop that are perpendicular to the magnetic field are going to contribute to the motional EMF that's generated by the generator. Okay, so the parts of these loops here that are kind of parallel to the magnetic field in some way, those will not contribute to the motional EMF. Okay, so only these links right here, these parts of our wire that do. So we've got two parts of our two segments here that are contributing to this motional EMF. So the total EMF that will be generated by this generator is 2 times the magnetic field times this length here times its speed times sine theta. And our angle theta is the angle between our velocity vector and the magnetic field vector. So here's our motional EMF again. It's just coming from these sides here, not the ones on top. Now we can remember that, this is from last semester when we were talking about rotational motion, that our angle around a circle is equal to our angular speed times time. Oh, that's what our omega is here. Now our linear speed is equal to the distance away from the pivot around which we're rotating and the angular speed. Okay. Now, also, so this R is the distance between the center of our rotation. So in this problem right here, we've got our loop. So our center of rotation is going to be in the middle of this loop here. And we're calling, kind of bad choice of variables, but anyway, we're calling the top loop width here W. So half of W over 2, that's R. That's the distance between the center of my loop and the edge. So that's what we have here. So then we can say that the motional EMF is equal to 2 times magnetic field times this length times, so V we could write as R times omega. Okay, could replace this V with R times omega, and R is W over 2, so we've got W over 2 times omega times sine of omega times time. Theta was omega times time. So then our EMF, these 2's cancel, is equal to, let's say we have a number of turns here, not just one, times magnetic field times the area, because the length times the width of our loop is the area, times our angular speed times sine of omega t. Okay, so that's the EMF that gets generated as we crank our generator. Okay, this EMF is going to oscillate. This is a sine function that's going to oscillate and look like this. That's where we get our alternating current, our alternating EMF. It oscillates between maximum values here. And the frequency, well, here's the period at which it oscillates. And our angular speed is equal to 2 times pi times the frequency, and then that's equal to 2 pi over the period of our oscillation. So we'll consider a problem where we will figure out the induced EMF and current of a generator. Now, an AC generator consists of 8 turns of wire, each with an area of 0.09 meters squared with a total resistance of 12 ohms. The loop rotates in a magnetic field of 0.5 teslas at a constant frequency of 60 hertz. Find the maximum induced EMF and current. And what is the maximum torque that must be applied to keep this coil turning in order to create the same EMF and current? We have to apply a torque, and we talked about torque in our previous chapter, magnetic torque. We have an AC generator. It has 8 turns of the wire that we're rotating inside a permanent magnetic field of 0.5 Teslas. The area of those loops of wire is 0.09 meters squared. The resistance of our total loops of wire is 12 ohms. And we are rotating these loops at a constant frequency of 60 hertz. Okay. So we want to find the maximum induced EMF and current by this generator. So our maximum induced EMF will come from this equation right here. We've got the number of turns times our area times the magnetic field times what we call the angular frequency. So the angular frequency is going to be 2 pi times this frequency here. And this number has a unit of radians per second. Okay? While this frequency has just a units of hertz, or an inverse second, 1 over a second. Okay. So our maximum EMF that we can generate with this alternating current generator is going to be 8 times 0.09 meters squared times 0.5 Tesla times 2 pi times 60 hertz. Okay. And then that's going to give us 136 volts. And I'm going to just go ahead and tell right now, because we'll use this later, that our angular frequency here is 377 radians per second. So you take 2 times pi times 60. That's 377 radians per second. So now we have our maximum induced EMF. So our maximum induced current is just going to be that EMF divided by the resistance. Okay. So that will be 136 volts divided by 12 ohms. Okay, and that's equal to 11.3 amperes. Okay, so if we wanted to figure out what was the EMF or the current at any time, not just whenever it achieves its maximum current or EMF, because this is an alternating current generator, then we can use the following equation, that the EMF at any time is going to be equal to the maximum EMF times sine of omega times t. Okay, so our EMF at any time we'll be able to find by using 136 volts times sine of 377 radians per second times time. Okay, so I plug in whatever time I want to here, and I'll figure out what is the EMF at that exact time. So this is going to look like a sine curve. It's going to look something like, we've got my curve right here. So the EMF is going to fluctuate between a maximum value of 136 volts and a minimum value of 136 volts, somewhere in here, depending on what time you're looking at along here. And the current also changes according to a sine function, and so you could find the current at any time would be equal to the maximum current times sine omega t as well. Okay, so that's one way you can figure out what is the current or the EMF at any time t. Now there's a second part to this problem, and that is what maximum torque must be applied to keep our coil turning. Because with the generator, you only generate this alternating EMF or alternating current if that loop is rotating inside the permanent magnetic field. And so in order to get this induced current or this induced EMF, what torque do we need to apply to keep our coil turning in order to keep getting this output? Well, for that, we can refer back to our equation for magnetic torque on a loop from last chapter. And that is going to be torque is equal to the number of turns times I times the area of those turns times B cosine, or sorry, times B sine theta. Okay. So the torque that we require is going to be equal to the number of turns times the current times the area times the magnetic field sine theta. So if we're looking for the maximum torque, okay, that we need to apply, then the maximum torque happens when sine theta is equal to 1, right? So the maximum torque required will just be our number of turns times the current that we induced, which I erased with that current. Maximum current was 11.3 amperes times our magnetic field of 0.5 Tesla. And so then the torque that we require would just be 4.07 Newton times meter. Remember, so this is 8 times 11.3 amperes times 0.5 Tesla times the area of my loop, 0.09 meters squared, in order to get the maximum torque required to keep spitting out that same EMF, and that same current is 4.07 Newton times meter. That's the unit of torque, Newton meter. What's the difference between a generator and a motor? Well, they're kind of each other, but in reverse. So a generator uses mechanical energy to create current, but a motor uses current to create mechanical energy. In a motor, you supply the current loop with current in a permanent magnetic field. Okay, and then because of the current within the permanent magnetic field, you can induce a torque. Here is a picture of what one of these motor loops looks like. Okay, we've got these lengths that I'm calling L, and then I've got the loop here, top of the loop here, and the bottom that I'm calling length W. And these loops are turning within a permanent magnetic field, and there's current running through the loop. Let's take this image and look at this loop from above. So we're gonna come up here with our camera and look down from above. And this is the image that we see. We've got the magnetic field running from left to right, and we're looking down. These are those vertical parts of that loop right here and right here, and they're both experiencing a magnetic force on them because of the current running through it and that permanent magnetic field. And that force, magnetic force, acting on the sides of these loops induces a torque. So you get in this case, a clockwise torque, okay? And then our loop orients itself in this direction here such that we have 90 degrees between the magnetic force vector and the magnetic field vector. And then once our loop keeps on rotating around such that it's oriented like this, the torque acting on those sides, those vertical pieces of the current loop, the torque acting on them becomes 0. And whenever our loop keeps on rotating clockwise in this way, once it rotates clockwise from this state here, then the torque is no longer clockwise. The torque becomes counterclockwise. So once we rotate past this vertical here, then the torque wants to switch directions. So on its own, if we don't change the direction of current inside the loop, okay, our electromotor is just going to kind of want to rotate back and forth, back and forth, back and forth. It doesn't want to keep on rotating around in a circle. So to keep the coil from oscillating around this orientation right here, back and forth, the current has to be reversed for half of the loop's rotation. You can do that by using an alternating current source, or you can do that by having a direct current source and somehow manipulating your device such that you get the current running through the loop to switch direction during half its rotation. So in lab, when we created our electromotor, what we did is we sanded off one side of each of those arms that connected to the posts to hold up the armature, so that during half of the rotation, only during half of the rotation, when the bare wires of our armature is touching the posts, will it send a current through the loop. And then whenever it rotates around such that there's no longer current through the loop, there's no longer any torque that's being supplied by the magnetic force. But our loop already has some momentum from the torque that it had on it whenever the arms of the armature were touching the posts. So what we're doing is we're essentially just turning off the current through the loop during half of its rotation. And that's how we can bypass this idea that if we keep the current running in the same direction in this loop, we're going to get oscillating motion. Now, a motor is essentially a generator, but in reverse. Generators convert mechanical energy into electrical energy, but motors do the opposite. They convert electrical energy into mechanical energy. So when a motor is doing work, its shaft is turning and an EMF is being generated. So the idea with a motor is that you supply it with EMF and it does some motions. Usually it may be a rotational motion. Okay, so that's still creating a torque. There's still going to be some EMF that's generated, okay, because of this motion. And so the input EMF that powers the motor is going to be opposed by the motor's self-generated EMF because it's rotating. This self-generated EMF is often referred to as the back EMF. So we could model our motor as something like this here. Here our motor is being supplied by a 120 volt external source. And then our motor, because the shaft is rotating, it's generating a back EMF. And our motor has some resistance to it as well. Okay, and this back EMF is like opposing that external voltage source that's being supplied to the motor to make it go in the first place. So the current through the motor with some resistance is then, we can get from Ohm's law, the current is equal to the EMF over the resistance, but this EMF is going to be the EMF supplied minus the back EMF of the motor itself divided by its resistance. So the current, for example, in this situation that I have right here, if the motor is supplied with a 120 volt external source, its motion on its own generates a back EMF of 70 volts. You subtract those, and so then the total effective EMF is less than what it's being supplied with because of its own motion. And we divide that quantity by the resistance of the motor, and then we get the current that's running through the motor.